Okay, so this is first lecture over chapter 18. So this chapter is over thermodynamics. So if we take a general reaction, so ammonia reacts with CO2 to make urea and water. So this is an important reaction industrially because urea is used as a fertilizer. So one thing that chemists always want to know is a reaction favorable or not, or is a reaction spontaneous. So if you just mix two chemicals together, will they react with each other or not? And so if you understand or know the energy in a reaction, then this can be predicted. You know, so that's what thermodynamics is. It's the study of energy changes in a process. So when I say process, it could be something like phase change, melting of ice, something that simple, or evaporation of water, or a chemical reaction. So we in chapter 6 of Chem 1311 was some introductory thermodynamics. And that's always the last chapter that I cover. So unfortunately last semester, which is when I had many of you, we didn't cover chapter 6 last semester, so we didn't get to any of the thermodynamics. So we'll review some of the basics in this chapter. This chapter reviews some of the basics anyway, of thermodynamics. Okay, so in thermodynamics, we'll basically be worrying about two terms, one H and one S. So H is what's known as enthalpy, and S is what's known as entropy. So enthalpy is the heat change. Heat change in a reaction, and entropy is a measure of order or disorder in a process or a reaction. So same with enthalpy, heat change in a reaction or a process. So we'll talk a little bit about enthalpy right now. So if heat is absorbed in a process, then the process is endothermic. If heat, and in this case, so enthalpy, so represented by the symbol H, and enthalpy is basically heat, which is often represented by the symbol Q. So if it's endothermic, then heat Q is greater than 0. If heat is given off in a process or chemical reaction, then the process is said to be exothermic and Q is less than 0, so Q is negative. Or if it's endothermic, Q or H H over Q is negative if it's exothermic. Okay, so that symbol stands for the standard heat of formation. Of a compound. So what does standard mean? So that the superscript 0 means standard. In standard state, so that means 1 molar if it's a solution, 1 atmosphere pressure, 25 degrees Celsius. So that means, so at 1 molar, 1 atmosphere, 25 degrees Celsius, how much heat is involved when you form a compound from its elements? So if this was water, for example, so if you were to form water from its elements, that would be forming water from hydrogen gas. So 1 mole of hydrogen gas and 1/2 a mole of O2 gas to make 1 mole of H2O. And that's what the F means, the formation. Okay, so for water, the heat of formation, and you always have to pay attention to the phase. Is it water gas, is it water solid ice, or is it water liquid? So if it's water liquid, the heat of formation from H2 and O2 is equal to negative 285.8 kilojoules per mole. So what does it mean that it's negative? Means it's exothermic, so energy is given off in this reaction. How much energy? 285.8 kilojoules for every mole of water that's formed. So then what's significant is delta H formation values for many compounds have been determined, and values put into tables so that you can use these values. So what do you want to use these values for? Well, will be for other reactions. So if we took this reaction of ammonia, for example, so 2NH3 gas plus CO2 gas to make urea, aqueous solution in water. So if you want to know what is delta H for this reaction, easy way to calculate that is to use this formula. Delta H is equal to the summation of the heats of formation of products minus the summation of the heats of formation of reactants. So you just look these values up in tables. So for example, in your textbook, Appendix C lists a whole lot of thermodynamic values. So if we just look in Appendix C of the textbook, you can see the heat of formation for ammonia is 45.9 kilojoules per mole. For CO2 is negative 393.5 kilojoules per mole. Urea is negative 319.2 kilojoules per mole. And water is negative 285.8 kilojoules per mole. And again, you got to make sure you look up the right phase, because if you look up H2O gas, it's going to have a different heat of formation. Okay, and so these values in the table are each for 1 mole. And so what you have to recognize now is that, well, there's 2 moles of ammonia. So that's what this N is referring to, is how many moles of each from the coefficient in the reaction. Okay, so if we just apply this formula for this reaction, so we take the products, so ammonia and water, and we're going to add those 2 heats of formation together, and then we're going to take the reactants, ammonia and CO2, add them together. We're going to take ammonia times 2, since there's 2 ammonia, and then add them together, and then we're going to subtract the 2. So delta H for this reaction is equal to the products, so negative 319.2 plus the negative 285.8. So this is for urea, for H2O, so we've got to do products first. And then sum the reactants. So we have 2 ammonias, so we got to take the 45.9 times 2, that's negative, and then add that to the negative 393.5. So if we calculate that out, so 6005 minus negative 485.3, and we get negative 119.7 kilojoules. So delta H for this reaction, so you don't even have to do the reaction in the lab to measure the heat change. You can just look these values up in a table and then calculate what the heat change would be. So if you went in lab and put in 2 moles of ammonia, 1 mole of CO2, let these 2 react with each other to make 1 mole of urea and 1 mole of water, this reaction would be, is it exothermic or endothermic? Well, it's negative, so it's exothermic. So this reaction would give off 119.7 kilojoules of energy. Okay, so just because a reaction is exothermic does not mean the reaction is spontaneous. And just if it's endothermic, that does not mean the reaction does not happen spontaneously. So we have to look at more thermodynamics to figure that out. But delta H is one of the important pieces of thermodynamics to help figure out whether a reaction is going to be spontaneous. Okay, so just because a reaction is exothermic does not mean it's spontaneous. The reaction may not be spontaneous, or if a reaction was endothermic, that does not mean the reaction would not be spontaneous. Endothermic reactions could be spontaneous. So if you want to know if reactions spontaneous or not, so enthalpy is one important piece to that, of the thermodynamics, but you have to have an understanding of the entropy as well to figure out. So if you have the enthalpy and the entropy of a reaction, then you can figure out if a reaction is spontaneous or not.